Rational and irrational numbers. Rational numbers can be written as a fraction. So let's look at some fractions. So for example, we've got the fraction 1/2. And 1/2 can also be written as 0.5. So here we've got an improper fraction and a decimal. These are both rational numbers. How about a mixed number, like an improper fraction, like 3/2, which can also be written as a mixed number, like that, right? It would be 1.5, which can also be written as a decimal, right? So we've got three different forms here: a mixed number, an improper fraction, and a decimal. These are all rational numbers. Let's look at another fraction, like 1/3. 1/3 can be written as a decimal. 1/3 is rational. And the decimal for 1/3 is 0.3333, right? It keeps going. So we can write that as 0.3, and we can put a bar over the 3 to show that it continues. So we've got lots of different types of numbers here. We've got an proper fraction. We have a decimal. We have an improper fraction. We have a mixed number. That's also a decimal, another fraction. And we have a repeating decimal. So the two decimal types that we have here is 0.5 is a decimal that terminates, right? It ends. And 0.3 with the bar over it is a decimal that repeats. These are both rational numbers because they can be written as fractions, right? And then along with the other types we have here, which is an improper fraction, proper fraction, and mixed number. All rational numbers. So what's not a rational number? Well, you may have heard when you learned about circles, area, circumference, of something called pi. Pi is a decimal that doesn't end and doesn't repeat. We always approximate, actually let me change this to approximate the value of pi as 3.14. But really, that decimal never ends and it never repeats. It goes on and on forever. There's actually people that enter competitions for how many digits of pi they can memorize because there's no pattern. And like I said, it never repeats. So this is an irrational number. Another time we get an irrational number is when we take the square root of a non-perfect square, like 12, for example. Let's pause and talk about what the perfect squares are. Perfect squares are the numbers that I get when I multiply a number by itself. So 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, 12 times 12. I can keep going, right? I'll stop there, but I can keep going. So these are all perfect squares. If I take the square root of a perfect square, then that means I'm asking what number times itself equals that. So that would be 11. If I take the square root of a number that is not a perfect square, then the answer to that radical is going to be an irrational number because it's going to be a decimal that does not end and does not repeat. So that would be irrational. This would be irrational. So 10 is one of those numbers that is not a perfect square. So if I try to take the square root of a number that's not a perfect square, it's going to give me a decimal that doesn't end and doesn't repeat. Irrational. We talked about pi being irrational, and it's about 3.14. If I add 2 to that, I get 5.14. But remember, it doesn't end there. It keeps going. So just because the number before the decimal is now a 5 instead of a 3, doesn't mean that the decimal doesn't change, right? The decimal stays the same. It still doesn't end and it doesn't repeat. So this is also irrational. The next one is a mixed number. We know that we can write that as a fraction right? 5 times 7 is 35, plus 2 is 37 over 7. So this is rational. Then we've got a terminating decimal, 25 hundredths, rational. And we've got the square root of a perfect square. Square root of 100 is 10. So this would be negative 10, also rational. 20 is not a perfect square, so that would give us an irrational number. It would be a decimal that doesn't end and doesn't repeat. Here we have a repeating decimal. Now, just like we saw with 0.333, right? That is rational because the decimal repeats. This decimal also repeats, so it's rational. Now, this last one is a little trickier because it looks sort of like it repeats, but then not really when you look closer. So I've got 1, 2, then 1, 1, 2, then 1, 1, 1, 2. I could predict that the next part's going to be 1, 1, 1, 1, 2, but I don't know for sure. But this is a pattern. This is not exactly repeating. So it is not a repeating decimal, and it does not end, so this one is irrational. So let's take a look at this decimal, 0.35. Now the way that we would say that, if we were saying the proper mathematical name, would be 35 hundredths. And if I want to write that in simplest form, I can divide the top and bottom by 5, and I would get 7 over 20. Right? Definitely rational. We knew that from the beginning, though, because it's a terminating decimal, and those are always rational. But how do we do it when the decimal part repeats? So I can't say that this is 57 over 100 because there's a bar here. This 57 repeats. It's 57, 57, 57. So the way that we do this when it's a repeating decimal is the number of digits that are repeating, we write over that same number of nines. So here I've got 2 digits that are repeating, 5 and 7, so I will put them over 99. This one I've got 3 digits that are repeating, so I would put them over 3 nines. 2 digits repeating, 2 nines. 1 digit repeating, 1 9. 3 digits repeating again, 3 nines. Now, if you had to simplify these, it's helpful to know the divisibility trick for 3 and 9, and it's a really simple trick. You add the digits together. So 5 plus 7 is 12. 12 is divisible by 3, so is 57. So I could divide top and bottom by 3 here to simplify if I had to. And the next one, 2 plus 3 plus 8 is 13, not divisible by 3 or 9. 6 plus 3 is 9. That is divisible by 9, so is 63. Also divisible by 3, but you usually want to use the greatest common factor, right? So 9 would be larger, so you'd be reducing by dividing by 9. And then in the last one, 3 plus 7 plus 4 would give me 14, not divisible by 3 or 9. So now we're going to compare these irrational numbers. And actually, yes, they both look like they're irrational, right? Because we're taking the square root of a non-perfect square. And on the right, we have a decimal that does not end and, well, maybe repeats. We don't know. If what comes after, because this part repeats, right? So if the next part is 007 and then it starts over again, then this might be a rational number. We just don't have enough information from what we're given here. So the square root of 55, you have to think about which 2 perfect squares that's between. So 55 is going to be between the square root of 49, right? And the square root of 64. And that is 7 and 8. So we know that the square root of 55 is somewhere between 7 and 8, but we don't know exactly where. But is 55 closer to 49 or to 64? It's a quite a bit closer to 49, right? So if it were right in the middle, we'd approximate it with 7.5, but it's not. It looks like it's closer to 49, right? So it's somewhere in this range. It's somewhere between 7 and 7.5. And then the decimal that we have over here, it starts out with 7.8 and then it continues, right? So 7.5 or smaller for the square root of 55, compared with 7.8, we know that 7.5 or smaller is less than 7.8. Let's look at this one. 7 goes into 29 4 times with 1 left over. So 4 and 1/7, we can get a decimal approximation for that using our calculator. So 1 divided by 7, I will show you what I got. So I'm going to write 4.14285 I'll round there, I'll stop. It keeps going, right? So that, but it is rational. The decimals for the sevenths, they take a long time to repeat, but they do eventually repeat, so they are rational. All right, and then we look at the square root of 17. Now, I could try to approximate it like I did with the last one. So I know that it's between the square root of 16 and the square root of 25. And I know that it's much closer to 16 than it is to 25. So it is definitely not 4.5. It's more like maybe 4.1. But this is also 4.1, right? So just approximating is not enough for this one. So I'm going to find the square root on my calculator. So I'm going to do 17 and then hit the square root button. And I got 4.1231056, and it keeps going, right? This one is irrational. This one is rational. But when I'm trying to compare them and see which one's bigger, smaller, here I've got, if I just look at the first few, I've got 4.12 compared to 4.14. So 4.12 is smaller. And then the last one that I've got for you is writing these rational and irrational numbers in order from least to greatest. So what helps, and what you saw with the last two examples, is for us to get a decimal approximation. So let's do that. So -9/6. I can reduce that a little and write it as 3/2, right? By dividing both top and bottom by 3. And I know that that's 2 goes into 3 once with 1 left over. So that is -1.5. All right, so I'm going to write that here, -1.5. 8.9 is already written as a decimal. Nice. Negative square root of 12. Now, the square root of 12, when you're approximating square roots, you want to think of what two perfect squares does it fall between. So it is larger than the square root of 9, but smaller than the square root of 16. And it's really close to half, right? It's only 3 away from 9 and 4 away from 16. So we know that it falls somewhere in this range. So I'm going to put, as an approximation, I'm going to put 3 point something, right? We don't know exactly what comes after the something, maybe 0.4 or 0.5, because it's really close to being right in the middle. All right, then the next number I've got is 6 divided by 3, right? 6/3, which is just 2. And then square root of 7, so I'm going to do the same thing. Square root of 7 falls between the square root of 4 and the square root of 9, which is between 2 and 3. And it's 3 away from 4 and 2 away from 9. So again, it's somewhere in this range, but looks like pretty close to the middle. So I'm going to put 2 point something. I'll just put a blank there, right? And then the last number is in decimal form already. So now here are my numbers. And now I need to put them in order from least to greatest. So when writing numbers in order from least to greatest, you want to start with the number that's furthest to the left on the number line. So that's going to be negative 8.3. That one is furthest to the left. I'm going to cross it out so I know that I already used it. Let's look for the next number that would be to the left of 0, right? We'll get all the negatives first. So the next number in the sequence would be this negative 3 point something, right? So negative square root of 12. All right, then I've got my one more negative number that's, left, which is negative 9 over 6, or negative 1.5. So negative 9 over 6 comes next. Now I've got my positives. So the smallest of the positive numbers is 2. So that's 6 over 3. And then 2 point something, which was square root of 7. And then 8.9. So now we've put them in order. We also compared rationals, irrationals, and we looked at how to write repeating decimals as fractions, and how to tell if a number is rational or irrational.